So I will continue what we started on in the very end of the last lecture. Specifically, so we'll show you the application of the systems of linear equations to the solution of the ODE, ordinary differential equation. Okay. So let us consider ODE. So we are this is given. X belongs to the interval from A to B, and we are trying to find function V and we also have the following boundary conditions. So essentially, these are conditions on the ends of the interval. So when it appears, for example, when you're trying to find the propagation, let's say you have a media and you are studying propagation of electromagnetic waves through media, or let's say neutron flux for calculation of the efficiency of the neutron protection for the nuclear reactor or similar things. So then you have an equation which describes. So okay, this equation is a little bit simplified, but it's really similar. It's pretty similar. So if you like, you can have a look one of my papers on the website, propagation through communication through plasma sheath. So which describes propagation of electromagnetic waves through the plasma sheath covering the re-entry space vehicle, like okay, practically any space vehicle or the warhead of the intercontinental missile. So okay, now so we have an equation, and we have also, it's a little bit simpler than what is used usually, but idea is completely the same. So we have boundary conditions. Let's say we have a equation describing the propagation through the media, and we have the neutron flux on the entrance of the media and some boundary condition that neutrons go freely on the other side of the media as well. Okay, then we are trying to find this function V. So how can we do this? So let me remind you. So first of all, we discretize our x-axis A, B, and we just split it into homogeneous grid. So with the same step, H, 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 H. So this I will number from x1, x2, x3, and so on. And the last one, xn, here is xn minus 1, and so on. So then this discretization can be described by the following formula. So this is nothing else but the step n. So k goes 1, 2, n. So n is the number of grid points. So this n minus 1 is because we have some extra grid point here. for example. Okay. Then, so what we do, essentially, if you remember, so v prime of x, you can write it as limit delta x goes to 0, vx plus delta x minus vx divided by delta x, right? So, so what we are doing in numerical computations, we are saying that, okay, let us consider fine enough grid. We will study it later in the end of the course. What does it mean fine enough? So how to control the error. So, and just approximately replace our derivative by the following ratio. Okay, so, but how to do the second derivative? So second derivative is just the derivative of the first derivative, right? So you can say that you just write it like that. But then for each of these terms, you can use this formula. And for example, in the following way. So pay attention that here I just used, instead of that formula, I used Vx minus Vx minus h divided by h, which is, as you understand, you can make step forward like here, or you can make a step backward here. It doesn't matter. So because these can be replaced, delta x going to 0, Vx minus Vx minus delta x. So this formula is just approximate variant of this formula. Okay, so as a result, I can write it like that. So if I will just, so they have common denominator. So if I put all these together, I will have this. Okay, now if I will remember discretization, so what does it mean? So if here, for example, I have xk, so grid is homogeneous. So xk plus h will be nothing else but xk plus 1, right? And here xk minus h equals to xk minus 1, right? Because of the homogeneous step. Okay, so as a result, I can write it as vk, approximately vk. Yeah, okay, I will introduce just for simplicity notation, the following notation. So function v at the point xk, I will call it vk. Vk plus 1 minus 2 vk plus vk minus 1 divided by h squared. Okay, perfect. Now, how can I write it? So I can write it, so I'm saying that I want this to be equal to g at xk or gk, right? Following my original ODE. Okay, so then this is what how I can write it: vk plus 1 minus 2 vk plus vk minus 1 equals to h squared gk. Okay, now Also, we have boundary conditions, and boundary condition, remember, is this, right? V at x equal to a equals to alpha, and this V at x equal to b equals to beta. Okay, according to this formula, if I take k equal to 0, to what? Sorry. If I take k equal to 1, so then xk is equals to alpha, right? Not alpha, a, sorry. And correspondingly, if I take k equal to n, I have b. So then it means that v1 is alpha and vn is beta, according to the boundary conditions which are given. Okay, now we can write this as a system of linear equations. So first, essentially it will look like that. So 1, 0, 0, and so on. 1, negative 2, 1, and so on. 1, negative 2, 1, so on. 0 here. 0, 0. So 0, 0, 1, negative 2, 1, 0, and so on. And here we will have further negative 2, 1, 0, then 1, negative 2, 1, 0, 1, 0, 0, 0, 0. So our coefficients matrix for the system will look like that. So so what it is, so this is our main diagonal. Really, let me draw it differently. So this is our main diagonal. Then we have subdiagonal, and we have superdiagonal. Everything else is equal to 0. Okay, and now we can multiply it by our values of our function on the grid, v1, v2, v3, and so on. And here will be vn minus 2, vn minus 1, vn. And this is equal to, so let us multiply the first row on this vector. So we will get just v1. We know that v1 is equal to alpha, the boundary condition, and everything else will be just corresponding values of the right hand side from here. And in the end, if you multiply this row on the unknowns, we will get just Vn. But Vn, again, according to the boundary condition, supposed to be equal to beta. So pay attention, because function g is given, so then all these entries, they are known, right? And alpha, beta, they are also given as boundary conditions. So the result, this vector is given. So this is vector of unknowns, and this is also given. Oh, sorry. Or we can say that we calculated that using our discretization. So that's it. So now what is interesting, we have so-called tridiagonal system. Tridiagonal system of linear equations. Why tridiagonal? Because you see we have main diagonal, subdiagonal, and super diagonal. Super diagonal. That's it. Everything, all other coefficients are equal to 0. It appears, so this is one of the examples of so-called sparse systems. By sparse systems, we usually call systems which have practically all entries in the coefficients matrix which are equal to 0, and only few diagonals or just diagonals and some elements which are not equal to 0. Usually it allows us to find the way of solution which is more efficient, way more efficient, and you will see it, than if you just form these coefficients matrix and apply standard LU factorization and use forward and backward substitutions to solve the system. So first of all, here you can see that you don't need to store the full coefficients matrix, because really all you need are these 3 diagonals, right? Only they are not equal to 0. As a result, so it decreases your storage by so essentially what is the, if this is n by n matrix, so how many entries you need to store the main diagonal? Could you tell me? Let us count. 1, 2, 3, 4, and so on. 5, or I mean not 5, n minus 2, n minus 1, n, right? So exactly n entries, right? Is it clear or not? In order to store main diagonal.
That's clear.
Okay, thank you. So, but we have 3 diagonals, right? We have super diagonal. Okay, it doesn't matter that it's n minus 1 or n minus 2 elements, doesn't matter. It's all of the order of n. So, and we have subdiagonal. So, approximately storage, approximately 3n entries for coefficients matrix.
Professor, really quick, what does the SLE stand for? Tridiagonal SLE.
System of linear equations. I used this acronym before, so but it doesn't. Yeah, please ask me questions if you feel that you don't understand something. Thank you very much for the question, because maybe somebody who is a little bit shy not ask that. So now you understand this. Okay, you see, storage requires 3n entries, right? For n, if you have n points, right? Instead of n square entries for full coefficients matrix. So this is huge. Believe me. So it just looks like okay. So now all of our computers have a lot of memory, so we don't need to think about that. Really, we do need to think about that. So because just recently I encountered the problem, computational problem, where I needed to consider a matrix with several tens of thousands of elements. And of course, matrix was stored perfectly, but I was unable to just get rid of all the elements completely. So as a result, my computational workstation, which has 128 gigabytes of memory, so gave me just the limitation on how large system can be stored in the memory. That's it. Because usually you need to store not just one array, but several arrays. Okay, so believe me, this is already important. Now, so you're saving a lot. So n is usually huge. So you're saving a lot of memory. And now, if you did any like serious programming, you know that modern computers, their bottleneck usually, if you need to work with huge arrays, is the memory bus. So the connection between the central processing unit and the memory. So you have to, which is RAM, I mean. So you have to write your code efficiently, or just do your code in such a way that you use less memory. Okay, now, so first of all, storage is an advantage of using special methods for sparse systems. So next, if we will consider just the following general tridiagonal system. And everything else are zeros. Zeros everywhere here. And let's say here we have x1, x2, and so on, xn minus 1, xn. Beta 1, beta 2, beta n minus 1, beta n. So essentially, this is matrix T, tridiagonal. This is my vector x, this is my vector b. So then we have Tx equals to b. Okay, now, one could use standard Gaussian approach for LU factorization, but really, we can try to represent our matrix T, just this matrix, in the following form. Okay, it appears that you can do this. So it appears that L matrix, unit lower triangular matrix, will have the following form. So essentially, it will be zeros here and zeros everywhere here. So this is our L matrix. You remember when we perform LU factorization, so here we always get ones on the diagonal. So it's a unit lower triangular. So, and for tridiagonal matrix, it appears that it will have this form. And this is what we will have. Let us try to look for our U matrix in this form. And then here we have Fn minus 1, Un minus 1, 0. And here is Un 0, 0, zeros everywhere here and here. So this is upper triangular matrix. So here, once again, have a look. We have main diagonals like that, right? And also we have here subdiagonal, and here we have super diagonal. Okay, so if we will multiply these, so we will get just these matrices, which are full of zeros, right? So then we will get the following, that U1 F1, L2 U1 L2 F1 plus U2 F2, and here will be L3 U2 L3 F2 plus U3 F3, and so on. So you have L n minus 1 U n minus 2. Here L n minus 1 F n minus 2 plus U n minus 1. Here is F n minus 1. And here is L n U n minus 1 L n F n minus 1 plus U n. Okay, zeros here, zeros here. Once again, you can see that you have super diagonal, main diagonal, and subdiagonal. So you got three diagonal matrix. Now, if you compare this matrix with the original one, this one, so here you have your subdiagonal, main diagonal, super diagonal again. Now, if you just compare corresponding elements here and here, you will get the following equations. D1 is equal to U1, E2 is equal to L2 U1, D2 is equal to L2 F1 plus U2, and so on. So essentially why you need it, and okay, let me write it. EK equals to LK UK minus 1, DK is equal to LK FK minus 1 plus UK, and so on. And in the variant, you have En equals to Ln Un minus 1, Dn equals to Ln Fn minus 1 plus Un. So why I'm doing this? Because have a look. So you had this tridiagonal matrix in general. Now I'm trying to figure out what will be LU factorization of this matrix. So I need to find these L's these U's and these F's, right? Because these are all non-zero elements. Okay, these ones I know. So here, this diagonal, main diagonal consisting only ones, I know. Okay, so if I will be able to express my L's, U's, and F's through corresponding these elements, as you will see, these F's will coincide with these F's. So then I've done LU factorization. Okay, let us do this. So, okay, this allows us to say that U1 is equal to just D1, right? So essentially, this element is equal to just this element. So now, next, from here, I can find that L2 is equal to E2 divided by U1. So E2 is this element, it's known, right? And correspondingly, U1 I already have found. So this allows me to find this element. Next, D2. So D2 is known, L2 already is known. So this allows me to find U2. So U2 equals to D2 minus L2 F1. So as you understand, L3 I will be able to find using similar metrics. So here is the same. So okay, UK minus not like that. So LK equals to EK divided by UK minus 1, which we computed previously. And correspondingly, UK will be obtained as DK minus LK from here, multiplied by FK minus 1. And so on till here, we are getting that Ln is equal to En divided by Un minus 1, which we computed previously. And here, the last Un equals to Dn minus Ln Fn minus 1. So essentially, you are starting from here and you are getting one by one all the coefficients. Pay attention that how many operations do I need here? So here, no operation. Here, one division, right? Here, I need multiplication and subtraction. But altogether, you can see that you need order n operations, or O capital N, because you have altogether how many unknowns? So you have n U's, so here n U's, and n minus 1 else. So altogether, and for each of them, you need just from 2 operations to 1 operation to compute, right? So altogether, you can say that you need some approximately 3n operations to compute all the coefficients. Okay. Now, what is interesting that So after you got LU factorization, right? So pay attention that you also have these simple L and U matrices. As you understand, instead of solving just standard backward substitution, right? So here it will be very simplified because of the simple way of representation, and this will be so. I can ask it as a question. So later, so just to derive the formulas for X through these L, U's, and F's and right hand side. So, but altogether also it will give you backward substitution, forward and backward substitutions. Substitutions will give you order n operations. So this is a good exercise to compute exactly how many operations it will be. So pay attention. How many operations we need to perform LU factorization, also called dense or full matrix, not sparse like we considering here. Just for n by n matrix. So how many operations we need approximately to perform LU factorization? I'm waiting.
Was it 2n squared?
No, for a dense matrix, n by n matrix. So we did it, so we had it. Okay. Two-thirds n cubed. Here, you can see that in order to perform LU factorization, you need approximately 3n operations. So difference is in this power, right? So let us consider n equal to 1000. Then here you need 2/3. Okay, 1000 is equal 10 to the third. Sorry. 10 to the third, so here 10 to the ninth operations altogether. So while here 3 multiplied by 10 to the third. Here 3000 operations. Here almost a billion of operations. It's a huge difference, believe me. So as a result, so just for LU factorization. Also backward substitution, but this is, I mean, not that important here because here backward substitution for full matrix is proportional to n squared, while here it's again proportional to n. That's it. So you can see that solving for a Tridiagonal matrix, not in a stupid way, just, you know, let us just create the full matrix, waste storage space and in memory, and then perform just full LU factorization. Instead of doing that, you can do this in a smart way, just using these formulas for LU factorization, and then just performing also in a smart way forward and backward substitutions. So, and then instead of n cube scaling for the solution of the problem with increase of the size of the matrix, you're getting just scaling proportional to n. It's way faster, believe me. So as a result, so I'm just, what I wanted to say, just for sparse systems, there exists a set of extremely efficient methods. So it's a good idea to take, for example, 464. This is where we study that, or at least some of the methods we study in 464. Applied matrix theory. But also there are more numerically oriented courses like numerical linear algebra and so on. So where we study efficient methods for sparse systems. MATLAB supported, by the way, so it has this special methods for sparse systems. So, but this is how we can solve differential equation. So what we have done, we started from the differential equation and then reformulated it in as a linear equation through discretization, right? We replaced our derivatives with approximate formulas. And as a result, we got the tridiagonal system. And we proposed an efficient way of solving this tridiagonal system for order n operations. So it's just one example when, so if you think that solutions of a system of linear equations appear only just in simple problems, like, for example, the balance of concentrations in chemical reactions, for example, or something like that, or just some dynamical systems. No, it's not true. So really, you solution of most of the differential equations can be formulated as a solution using these finite difference approximations, for example, can be formulated as a solution of system of linear equations. So the result, I just wanted to tell you that we are just performing, we can do this in a very efficient way. And systems of linear equations, so essentially linear algebra, numerical linear algebra, solution of systems of linear equations, is the base for most, not all, I have to say, for example, spectral methods are different from the first point of view, but really they also can be formulated as a solution of system of linear equations. So practically all the time we are coming to solution of systems of linear equations in numerical analysis. As you will see later, the same will work for polynomial interpolation and many other things. Okay. Okay, so that's it. So all this information, by the way, you can find in Linalc 2 lecture, so which is available on the website. So now, because I already covered Gaussian elimination without pivoting and even with pivoting, so I propose you, but I used information from your book rather than from the lecture notes. Please have a look at the lecture notes, so it's useful. So you can just, maybe you will understand Gaussian elimination better as a result. Okay, now all I want to say, so essentially this is what we are doing. We are considering matrix A, and let us forget about pivoting for a second, right? Or okay, let us say we use pivoting, PLU. So, but pivoting essentially tells us how we exchange rows, right? Row permutation rows. permutation matrix. So, which essentially means that this matrix P does nothing else but just permute rows. I have shown you that really what you can do, you can just, I have shown you that permutation matrix inverse to that is the same matrix, right? Because you're just swapping two rows, right? This is why you can multiply like that. And as a result, you will get PA equals to LU, right? So, so essentially, when you perform permutations, this row swapping on the matrix A, you essentially just renumbering the rows. So as a result, P just contains numbers of rows in some order. So in order to store that, you need for n by n matrix. So all you need is n integer values, which will be just numbers of rows starting, for example, from 1 to n. In some order. That's it. Okay, now LU. L matrix has the following form in general, not for tridiagonal system, but in general. It has ones on the main diagonal and some elements here. Here you have no elements at all. U matrix, as you remember, when we do Gaussian elimination, it has U11, U22, so it has diagonal elements, some elements on top because it's upper triangular matrix, and zeros here. So from here, you can see that L uses this part of the matrix, while U uses this part of the matrix. So L uses all elements below subdiagonal, super diagonal, I mean main diagonal, while U uses main diagonal plus everything built above. So this is why really you need no more than your original matrix A. So you can represent it, okay, not like that, not A. So LU, product of L and U matrices, you can store as UN and upper elements, just this, and this thing you can store here. So n by n elements for storage. So plus n integer elements array. So as a result, this is what is done usually. So you just provide A to LU factorization subroutine, and it will give you L and U in the same storage as A. So it essentially, instead of A, you will get, after this LU factorization subroutine, you will get L and U consisting of elements U and L packed in the same array, plus of course an integer elements array for permutation matrix. So which is just a renumbering of rows. Now, really, as I told you before, nobody really shifts, move any elements. So usually you just renumber them. Okay, so by that, I would like to conclude our study of numerical linear algebra for this course for a second. So really we will study a little bit more about least squares and QR factorization, but it will be later. So now we shall study a new topic, which is Introduction to Interpolation. Okay, so idea is the following, that usually so before we considered this in the beginning of the lecture, we considered solution of this differential equation of this one, which is on the top here. So we considered solution of this differential equation, and as a result, what we have got, so we introduced first of all the grid, right? This axis. And then we, as a solution, we got the value of our function v in the corresponding, so this vector, which is values of our function v in the nodes of the grid, right? So correspondingly, we, instead of the analytic function, of course, we got just some numerical values, just numbers on the grid, right? So pay attention, we started originally from the problem which was formulated for some function, right? So we were given this function g, right, which is just some, usually just function. In some cases, it can also be given as a function on a grid, but in many cases, it's just some analytic function. So, or just some function, yeah, expressed in analytic form. So here we have boundary conditions, but as a result, instead of getting also just some answer in the form of function given as a formula, right? Instead of that, you're getting your solution on the grid. So in other words, we can formulate it in the following way. So we have a data set like that. Xi, yi, pairs of numbers. I goes from 1 to n. For n strictly more than 0. So in other words, let me draw it differently. In other words, let us suppose that this is our A, B, and we have some grid, not necessarily homogeneous. Yeah, by the way, this tridiagonal approach, it can be generalized on non-homogeneous grid. I just don't want to do this right now. So if you're interested, please come to the office hours and I will show you how to do this. And then, so this is x1, x2, x3, and so on. Xn minus 2, xn minus 1, xn. So, so let us suppose that we got solution of our differential equations in the form of the grid function on the grid, right? So, and this is correspondingly y1, y2, y3, and so on. And here is, yeah, that has to be line yn minus 2, yn minus 1, yn. Right? So we got these pairs of numbers, x1, y1, x2, y2, and so on till xn, xn. Oh yeah, we use here n capital. xn, yn. Okay, it looks like, okay, we are great. So we found the solution of the system of linear equations, which describes our differential equation and so on. So we were able to find it. The only problem is that what if I need, so if I have this grid function, so function defined on a grid, so this set of data points, but what if I need to find the value of my function somewhere between these data points? So how to do this? Of course, I can say that, okay, let me consider, so I can draw a function through these points with my hand, for example, right? And then it will give me just some approximate value here, right? The problem is you can formulate this problem like that. So if you have x, how to find f of x, right? So essentially you want to replace this set of these discrete points with some function, some continuous function, which will give you ability to find values of the function everywhere between the points. So the question is that, okay, how to find it? So you know that your function is passing through all the points. So really, it's not that necessary, but we will later consider, when we will be considering least squares, I will show you that this condition can be eased. So, but for now, we consider the situation when these points are real exact points. And I have values of my function given in these points. So question is the following: how to find the function passing through all these points, data points, in analytic form? Of course, we need to make some, we just need to suppose what our function will be. So, for example, let us consider let us consider data set consisting of 2 points. So don't forget, this is x1, y1, x2, y2. So I have data set consisting of 2 points. Okay, great. So could you tell me what curve I can always draw through these 2 points? What kind of curve?
The linear line.
Just a straight line, right? Okay, so essentially I'm saying that let me consider p of x, which will be ax plus b, right? And then I can, by the way, have a look. I can do the following. I can substitute. So let's say a multiplied by 0. So I'm substituting x equal to 0 plus b. And this has to be equal to what? Yes, to 2. Okay, now I have, in the second point, I have x2 equal to 2, right? I substitute in x2 here. And this has to be equal to y2, right? Which is equal to 4, right? So I got a system of 2 linear equations, right? So I can solve it. So for example, here, from here, I will get that beta b equal to 2, right? Immediately. And then I substitute it here. I'm getting 2a plus 2 equals to 4. Correspondingly, I got that a equals to 1, right? So I got p of x equals to x plus 2. Right? Clear or not?
Clear, clear.
Yeah. So I was able to find a line passing through these 2 points, right? Okay. Could you tell me if I will consider 3 points? So what kind of curve I can always draw through these 3 points?
Problem.
Right. So let me consider example 2. Let me consider p of x, which will be a2x squared plus a1x plus a naught, right? So, and I'm given x1, y1, x2, y2, x3, y3, right? So I know that I can always draw a parabola through them. So why it is so? So let me substitute first x1. a2 x1 squared plus a1 x1 plus a naught, this has to be equal to y1, right? Now let me substitute second point. a2 x2 squared plus a1 x2 plus a naught equals to y2, right? And let me substitute third point. a2 x3 squared plus a1 x3 plus a naught equals to y3, right? So what I've got, so these are these, and these are known, or you can say given, right? And these, all y's, are also given. So as a result, I'm getting system of linear equations for A0, A1, A2, right? Which I can solve again, and then I will get my interpolating, so-called interpolating function. Okay, now I just have shown you this, but now let me remind you some linear algebra, and then we will formulate more general case. So definition 1. Linear independence of vectors. So let V I goes from 1 to n, be a collection of vectors. We say that the collection is linearly independent is linearly independent if the only solution Ci, sorry, goes from 1 to n, 2 linear combination like that equals to 0 vector is the following. The only solution is the following: C1 equals to C2 equals to, and so on, equals to Cn equals to 0. That is, vector C is the 0 vector. So in definition 2, linear independence for functions. So a collection of continuous functions I goes from 1 to n, defined on the interval I, which is included into the set of real numbers, is linearly independent if the only solution Ci goes from 1 to n, 2 C1 phi 1 of x plus C2 phi 2 of x plus and so on, Cn phi n of x equals to 0. Is C1 equals to C2 equals to, and so on, Cn for any x belonging to our interval. So pay attention. This is any or all x's, if you like, belonging to the interval. So, which means that our C vector consisting of these entries is the 0 vector. Okay, I will stop here.